I want to talk mostly about the written section, but I'll throw some hints about the multiple choice section. This is your biggest test of the year. It's worth 16%. You know what? Please, keep them all the way off. You can really think about this as on the Earth, in orbit or in space, and horizontal and vertical. So I broke this down. What are some fair game questions on the Earth? You know that I'm nuts about amusement park rides, so one I might try and throw at you is something like this. It says a frictionless cart rolls down an incline and then loops the loop. This is from your review. I'm just going to change the numbers and walk through the derivation. You might remember the lovely answer, and if you remember the lovely answer and you can go straight to that shortcut if you see it on the test, well, that's great. But here's what I'm going to do. I'm going to make this 12 meters, which would make this 24 meters, and now it's a whole new question. It says, from what minimum height h should the cart be released so that it does not fall off the circular track? Key is to talk or to look at right here, top of the loop. What are the forces acting on this? Get the obvious one. Gravity. What else? Into the center, upwards or downwards, normal force. Okay. If it was a Ferris wheel, it would be upwards, but since we're a roller coaster, we're going to be downwards. And really what we're then saying is the normal force and gravity has to equal mv squared over r. How do I know they're a winner? Our rule was the net force, the winning force, if you're moving in a circle, is always pointing toward the center. Okay? Now, the fact that they said minimum height tells me that I can assume the normal force is 0. Or, Trav, they could have told me so that you have a normal force of 50 newtons. I just put a 50 in for the normal force. They could have given me more information. Or they could have said so that you feel 1g, then I would let the normal force equal mg, and I would put an mg there. Or they could have said so that you feel 2g's at the top of the roller coaster, I would have put 2mg there. Here, minimum normal force means I wouldn't want to feel anything. So I get that there. mg equals mv squared over r. Now they want the minimum height. I'm going to come back to that. The minimum height, if I call this initial and this final, there's a change in height, there's a change in speed, there's a curvy path. I could say ke initial plus pe initial equals ke final plus pe final. In fact, I think when we did this question, we started here and I wrote the circular, we started with this, and I wrote the circular motion part later, because we said height, oh, this has an h in it. We're on the Earth, Clay, so I can use mgh. I don't need to use the cosmic potential energy, and I think we're going to assume we're starting from rest. So we said mgh initial equals a half mv final squared plus mgh final. Kiowa, is there a lowercase m in everything? Then, hey, mass cancels. That's kind of cool. We wanted to get the h initial by itself, so we said you could go gh initial equals g final. And we noticed in this equation, I get mg equals mv squared over r. We said, you know what? Turns out v squared equals gr. Now normally I'd take the square root of that, but since I have a v squared right here, we said, oh, cool, can do that. Kiowa, is there a lowercase g in everything? Yeah. Strangely enough here, this canceled. This doesn't mean that this will work with no gravity. What it means, Lewis, is this will work on any planet. The g of the 9.8 of Earth is not applicable. This would work on the moon with the same height and the same track. And so we ended up with the initial height being half of the radius plus the final height. But then we said the final height from here to here, although it's 24 if you want to generalize it, the final height was just twice the radius. And this is where we ended up with that lovely, your initial height is 2.5 times the radius, which in my case will be 2.5 times 24, 30, yeah, 36.
If you were really bad and decided on the test to use some...
Sorry, I got to cut you off. 24 times 2.5 is going to be 48 and 12. It's going to be 60. Now I can, sorry, but I can't leave the wrong answer for the YouTube people. So this would be 60 meters. Now what? Ask?
If you were really bad and you accidentally used the gravitational universal constant,
The problem you would find if you used big G, big M, little m over r for potential energy, you would find that the radius of the Earth is so big that that difference between here being 24 meters higher than the radius of the Earth and here mystery height, your calculator wouldn't be able to track that many sig figs because it's such a small, because remember, it's 6.34 times 10 to the 8th, or times 10 to the 6th, and you're talking about that 24 way over there making a difference. I have a feeling when all was said and done, your calculator wouldn't notice any difference. Did that answer your question okay? Simple reason, simple, by the way, simple concept. You're on the Earth and you're staying on the Earth, use MGH. That's why I kept saying, are we going cosmic? Are we in space? Then we use the cosmic one, which is going to come later. So this might be fair game. Also, fair game would be going backwards. What if I gave you the initial height? If I gave you the initial height, could you find how fast you're going at the top and then figure out the normal force? I think so. Another on Earth question. This is a horizontal question. Doing something with going around a corner. So we said if you're going around a circular corner, your free body diagram, yeah, Trevor, we do lots of free body diagrams in Physics 12 too. This is very similar. I always drew the free body diagram as a front view facing me, and we assume, let's pretend that the car is going around the corner this way. What are the forces acting on it? Get the obvious one, Ty.
Gravity.
What else? I agree. What path is this car tracing out?
Circle.
So there has to be a force pointing towards the center. Now, look up, all of you. FC never shows up on your free body diagram. If you're not sure, if you don't know what force goes there, don't put FC. That's going to be wrong, I guarantee it. It's going to show up in my equation when I go winner minus loser. What force is pushing a car around a circle?
Friction.
Convince me.
Because if you're on ice, it'd be
Yeah.
slide.
One, again, handy trick. If I'm not sure what force it is, I always say, well, what if there was ice there? If it doesn't work, the mystery force is probably friction. So we have this. Friction is what's pushing me in a circle. Trevor, friction is what times what? I've never said mu times mg ever. Mu times the normal force. And that's going to equal either m4 pi. Well, you know what? It's going to equal mac, where ac is either, Travis, 4 pi squared r over t squared, or it's v squared over r. Which one am I going to use here? Well, they gave me a speed. I'm going to use the v squared over r. So I would get mu. Trevor, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? Mg. But I've never said friction is mu mg. It's mu times the normal force, and then go figure out what the normal force is. If it's a boring question, it'll be mg. If it's a more interesting question, Physics 12, it'll be on a slant. It was parallel and perpendicular and all sorts of good stuff, right? I can say that, and it's going to be mv squared over r. And I'm just going to pause here. Yeah, big trucks and small cars can go on the same roads. It seems to me, Kohei, here I'm asking you to find the minimum coefficient of friction. How would I get the mu by itself here, Kohei? Divide by g. I would also have no problem giving you the coefficient of friction and saying find the maximum safe speed, get the v by itself, or giving you the coefficient, giving you the speed limit and saying if we're building this, what do we have to have the radius to be? In other words, all of those are fair game. Or, hey, I could even move you to a different planet, give you the speed, give you the radius, give you mu, and say find g on the mystery planet. That would also be fair game. So all of those are fair game. Is that okay? What else can I do on the Earth? Ferris wheels. Ferris wheels. So I can tell you, for example, that the period is, I don't know, 36 seconds. That's a little slow. 16 seconds. That's a little more realistic. And just to make this different, let's make the radius 18 meters. And I could say Find the normal force at the top. Find the normal force at the bottom. Hey Kyle, what do I call those little vertical marks? You learned something new. All right. The difference between the Ferris wheel and the roller coaster is on the Ferris wheel, your head is always pointing up, which means at the top, the normal force is in a different direction than at the bottom, relative to the circle. Let's do the top. Lewis, what are the forces acting on the top? Get the obvious one. What else? Which way? Bigger, smaller, or the same size as mg? How do you know? Because I'm moving in a circle and my net force has to be pointing towards it. So really, I should have been I should have done that if I'd been really clever. What's my equation going to be? By the way, Trevor, you're hearing winner minus the. You notice a lot of what I'm teaching you in Physics 11 works for Physics 12 as well. We just expand it. Give me my equation, Lewis.
mg minus fn.
4 pi squared r over t squared. How would you get the normal force by itself? Subtract normal force? I think I would add. I think I would go plus that there and minus that there. We've done this dance before, have we not? I think I would go mg minus m 4 pi squared r over t squared. Lewis, at the top, will you feel lighter or heavier? And convince me. Will you feel lighter or heavier at the top? Convince me, folks. Sorry, what was your answer? Convince me. Well, normally, what you feel for the normal force is just that. All of you right now are feeling mg as your normal force. Turns out, here, you would feel at the top, you'd feel mg minus something. You'd feel lighter. You'd feel lighter. Have I given you enough numbers? I don't think I gave you a mass of the person. I need to tell you that the person's mass equals, I don't know, 63 kilograms. Okay. By the way, does the little m cancel here? No. And this is why I think I've told you, little kids can handle anything without throwing up easier than older, heavier people are, can handle. We feel the effects of the changing normal force more than little kids. As you get older, you may find that you can't handle the same rides as you could when you were younger, that your stomach starts to churn a little bit more. It's the great circle of life, Simba, the great circle of life. Before I go further, I would also have no problem telling you the normal force and saying, what's the period? From this equation here, you would probably crunch this as one number, and then get the t by itself, times the t squared here, move this number down there, square root. What about part B at the bottom? Trevor, coming at you. What are the forces acting on this person right here? Get the obvious one. Which way? I agree. What else? They're sitting in a chair, so the chair is pushing up, the surface is pushing up. What have we called that in Physics 11? We called it a normal force. Now what we learned in Physics 12 is, what path is this person tracing out, Cade? So when you're moving in a circle, where must your winning biggest force always be pointing? Toward the... So that's how I know the normal force is bigger. By the way, that would also be a convincing proof for why you feel heavier at the bottom, because normally you just feel mg, but I know the normal force has to be bigger because it's what's pulling me in a circle. My equation here would be normal force minus mg equals m 4 pi squared r over t squared. How would I get the Fn by itself? I'd plus the mg over. Is that okay? Yeah.
For A, you did, you kind of swapped them around.
Yep.
So why didn't you do that for B?
What am I trying to get by itself in part B?
FN?
What's in front of the Fn right there? A negative?
Positive?
Then why don't I leave it and I would just simply plus that over and I'm done.
But for A,
Yep.
you switched, can you just add mg?
No, what's in front of the mg? What's sitting right there in front of the mg? A positive. So how would I move the mg over? Minus it, but that would give me negative normal force, which I don't think I want.
Okay.
And So this is what we've been doing in Physics 11 quite a bit, is I've been saying, look, if what you want to find has a minus in front of it, move it over, and at the same time, move the other stuff over to this side by minusing or plussing them if necessary. It's a great little trick. The third thing, the gravitron, okay? Let's do the free body diagram right there. What are the forces acting on this person? Get the obvious one. Which way? Gravity. Which way? Down.
Oh my god.
Down. Oh, Colin, do I need to use big G, big M, little m over r squared for gravity? Not in space. Probably could and get away with it, but it'd be a lot of extra typing. Is this person sliding down? Are they sliding up? So there has to be a same size force pointing up. We're not sure which one that is. Let's come back to it. What path is this person tracing out? So there has to be a force pointing inwards. Most common mistake I see kids do this. Does FC ever show up on my free body diagram? What force is pushing you in a circle? The wall, the surface. Trevor, what do we call the force from a surface like the ground or a wall? See, Trevor? You can handle some of this. The normal force is what's pushing you in a circle. Which, now that I've written that, I can take a good guess. I think I know what that vertical force is. What is that vertical force? Friction. And what that also tells you, by the way, I guess, is that surface that you're leaning against does play a role in this. Does play a role in this. So what could I ask? I could say something like, if the period equals, I've never been on this ride to my shame. What would, you know what, let's go, how about every 1, 2, that's too slow. It goes faster than that. If the period equals, how about 2.4 seconds, find mu. Lots of things go into 2.4. Half the time when I make up numbers, I'm trying to make them work out nice. 12s and 24s, lots of things go into those. Find mu. Okay? Or I could give you mu and say find the period. Or I could give you mu and I could say find the speed. What's my equation going to be here? What path are we tracing out? So what's my equation going to be here? Yes, right there. Normal force is what's pushing me in a circle. Normal force equals m4 pi squared r over t squared. Right? I don't know the normal force. And I can't say, oh, but look, I don't know this force, because I would need to know that one, and I don't know that one. So, let's write another equation. There's another equation I could write, the equation that runs this way. What's the equation that runs this way? Equals what? Are we sliding down? Are we accelerating up? In fact, it equals 0, or if we really, really wanted to, this is fundamental stuff right here. This is what's going to be on your test right here among some of these things that I've been showing you right here. This is from the homework right here. That has to be true, otherwise you couldn't go on the ride. You couldn't be sliding up and you can't be sliding down, otherwise the ride wouldn't be safe. Is that okay? Yeah. Ah! You ready, Kohei? Gonna make it? Because you're looking a little bad there. Otherwise, maybe you want to borrow the little eye thing from Colin and just go right to sleep and you can cover your eye. You gonna make it? Okay. Trevor, friction equals what times what? Redeem yourself. Hey. I don't know the normal force. Oh, but look. I can get the Fn by itself in this equation. How would I get the Fn by itself? Over here, how would I get the Fn by itself? So, in this weird equation here, we get mg over mu. It's a little strange, mu's on the bottom, but it must be, equals m 4 pi squared r over t squared. Hey, when you went on, anybody here been on the Gravitron? Did they make you step on a scale before you got on? Why not?
Because M's cancel.
Yep. What did I say we wanted to find here? We wanted to find mu. I do have one fraction equals one fraction. Stuff moves diagonally. Okay, so I could say, what's it going to be? Mu equals gt squared over 4 pi squared r. I would need to give you r, so let's say that the radius r equals, you been on the Gravitron? How far all the way across, roughly?
Like 6 meters?
Further than from you to me?
All the way across?
Yeah. Yeah? Further than,
Probably be like this way for the radius.
okay, so let's say 4.2 meters. Okay? And you could now get the mu by itself. You got everything. Period. G, 9.8, and R. Or, if I gave you mu, could you get the t by itself? Sure. The 4 pi squared r would move up to here. The g would move down to here, and how to get rid of a squared? A root. Or, if instead of giving you the period, I could have given you the speed, in which case it would be mv squared over r, and I'd muck around with that. Okay? But there's going to be, on land, there's going to be a car going around in a circle, and then out of roller coaster, this ride, and I showed you 3 things. Oh, Ferris wheel, 2 of those 3. Okay? Either written or multiple choice or both. Is that all right? Now, what won't I ask? For vertical circles, I will not hit you here or here. Too yucky. Too yucky. Space. Key idea, or one of the key concepts, is this notion of gravitational field strength. What equation does that calculate? What force does that calculate?
Gravitational field strength.
That's not a force.
Sorry.
You guys are way overcomplicating this.
Force of gravity.
What?
Force of gravity.
What?
Force of gravity.
That's gravity. How do I know it's not potential energy? Not negative, and it's got an r squared in the bottom. I know, they look alike. Deal with it. Hey, what force does that calculate? mg. What does that calculate? So they must be the same. Now, this is the universal one. This is the local on Earth one. But if you want to find the gravitational field strength universally, the m's cancel. You get that. You know what? I'll leave the m's in, and I'll show you that they cancel. In other words, I'm going to be talking about gravitational field strength, and I hope you know it's that. This is measured in meters per second squared, if you're talking about accelerating at 9.8 meters per second squared, negative, you want to call it down. Or it's measured in newtons per kilogram, because G equals force divided by mass from that equation, newtons per kilogram. See it? And it seems to me then I can, using this, if I give you 2 of G, big M, and R, you can find the third. Big G is constant. What's big G? Always, anywhere in the universe, even in a black hole. 6.67 times 10 to the 11. That's what we need to put in this equation so that we get an answer in newtons. The same way as you need to multiply seconds by, or divide seconds by 60 to get an answer in minutes. The same way as you need to multiply hours by 60 to get an answer in minutes. Here, I got to multiply by big G if I have two masses and a meter squared on the bottom. That's what gives me my answer in newtons. And that just happens to be the constant. It's what it is. I did talk about how it's really small, which is why it took so long to find. So if I give you the gravitational field strength in meters per second squared or newtons per kilogram, and then I say, hey, find the mass of the planet. If I give you the radius, you can find the mass of the planet. In fact, we did that in our notes. We did that for the Earth. This is how we found that the Earth is 5.98 times 10 to the 24th. And I think I said to you, the first thing that Cavendish and others realized is, oh, that's heavier than we thought. Maybe it's not dirt all the way down. Maybe there's something denser down there. This is our first idea that there's an iron core. There's other reasons why we believe that as well, but that was the first inkling that there's a dense iron core at the center of the Earth. Okay. So this is gravitational field strength. Key concept number 2. Orbit. Unless I ask how much work? Question mark. If the question mentions orbit and doesn't mention work, then what's our starting point always been? No. Gravity is what's pulling me in a circle. Okay? And from here, we can derive any equation. We can go with big G, big M, little m, all over r squared equals mv squared over r. That means if you give me the speed, I can find the radius, or if you give me the radius, I can find the speed. We would say, yay, yay, and one of those cancels with that. Or we can go big G, big M, little m over r squared equals m 4 pi squared r over t squared. Again, the mass cancels. Does an r cancel in this one? No. So we ended up with, if I get the v by itself from this equation, we ended up with v orbit equals the square root of big G, big M over r orbit. I never memorized that one, although I end up rememorizing it every time I teach this unit, but I'll forget it again in a month or so. The other two are more complicated. I've never memorized. We could get the r by itself. We could go r cubed equals big G, big M, t squared over 4 pi squared cube root. By the way, I could also get the r by itself here, which is pretty easy. The r moves up here, the v squared moves down there, and you're good to go. So if you know the speed in orbit, you also know your orbital radius. Or I could get the period by itself, which would be t squared equals 4 pi squared r cubed over big G, big M. How to get rid of a squared square root. So what I've said to you is if I give you any one, you can find the other two. Okay? Read carefully. Is the information given a radius or an altitude? Read carefully. There is going to be one question, I think, on your test where I give you the altitude, and you'll have to add the radius of the planet that we're orbiting around. Okay? You guys are okay on that? Yeah? But don't always assume you have to add the radius of the Earth. If I give you the radius in orbit, you don't have to add the radius of the planet. You already got it. You're good to go. Less work. I'm guessing that these ones you folks are okay on. What I'm going to spend most of my remaining time on is work and energy in space. Okay? When do I use conservation of energy? And the answer is finding a radius, a speed, or an altitude. There's even an easier answer than that. If they don't ask about work, try conservation of energy first. If the question doesn't mention work, try conservation of energy first. Okay? So, let's make one up. 4,500 kilogram rocket is launched from Earth with an initial speed of 6,500 meters per second. Let's bump it up. Escape velocity, I think, was 11,000 or something like that. So let's go pretty fast. Let's bump it up to 8,500 meters per second. Let's go like this. How far will it get from the center of Earth? Okay. Colin, are we going cosmic here? I think so, so I'm not using MGH. Did they ask me about work at all anywhere in this question? What did they ask me to find? I think R. How far from the center of the Earth? R. Did they ask me about work? No. This is a job for conservation of energy. And I'm going to go all the way through this because I think a number of you aren't sure how to handle these ones on the final couple of steps. So we would go like this. K E initial plus P E initial equals K E final plus P E final. Trevor, we're going to be doing this unit probably next in Physics 11 after spring break. The only issue is we're doing the cosmic one that works anywhere. The version of this that we'll be looking at only works near the surface of the Earth, but we won't go into space this year anyways. I think it implies that the final kinetic energy is zero. It's going straight up, it's slowing down, 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 and it just reaches its furthest point from the Earth. So I'm going to go a half mv initial squared plus mgh initial equals, oh, no, Mr. Dewick. We're cosmic. Plus negative big G, big M, little m, all over R initial, which I think is R Earth, equals negative big G, big M, little m, all over R final, which is, I think, what I want to find. Normally, I would try and get the R final by itself. This is ugly enough that I'm not going to bother. Instead, and I think Colin, you and I were discussing this earlier today, I'm going to crunch this whole thing, get an answer, and then I'll solve for R final. I'll get the R final by itself. So I'm going to say, oh, Kiowa, is there a little m in everything?
Yeah.
You're with me, right? You're not foolishly on your phone or anything like that? No, that would be so. I get 0.5, oh, don't want red, Mr. Duke. 0.5, 8,500 squared plus negative 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, all over. So the radius of the Earth, 6.38 times 10 to the 6th. That equals negative big G, big M, little m over R final. By the way, if I'm finding a radius, will my answer always be positive or negative? If I'm finding a radius, a length, positive. So I'm going to expect, Cade, that this whole side works out to a negative, so that when I have a negative and a negative here, what will I end up with? Positive. If I don't get a negative, I'm going to worry. And I'm going to go to my calculator. Unfortunately, my nice one doesn't work. I'll have to go with this one. Pardon me? It's crashing every time. I don't know. I got a bunch of wonky stuff going right now. Menu. Negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 20. Whoop. Times 10 to the 24th divided by 6.38 times 10 to the 6th. You know what? I think I can just go plus a half times 8,500 squared. I can do this in one step. I get negative 625,181,181.8, negative 625,181,181. Oh, this is wrong. That's, yeah, the square didn't go. That better? Negative 2639,3182. Negative 2639,3182. 393182. Good gravity over there. And I shouldn't have written this M here because I canceled out the M, didn't I? Sorry. Come on. And this is what I was getting at earlier with that R final. Now, how would I get the R final by itself? I think I could times it to here and divide that to there. R final is going to be negative big G big M over negative 26393182. It's going to be negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by, and I think I can even go answer button. There's my final radius. 1.5 times 10 to 1.51 times 10 to the 1, 2, 3, 4, 5, 6, 7. This will get me a fair ways up there, but not enough to leave Earth's gravity. 1.51 times 10 to the 7th meters. What if instead of asking you to find the distance from the center of the planet, which is what I asked, how far will the rocket get from the center of the Earth? What if I asked you to find the altitude? What would I do with this number now?
Take away the radius.
Take away the radius of what?
Earth.
Earth. Okay?
For the said object.
So that's what I would do, but I'm not going to do that. Is that okay? What else could I do with this same setup? Oh, instead of launching from the Earth with an initial speed, I could tell you how high we started, how fast will it hit the Earth. Now you'd be solving for V initial. But you'd start out with a very, very similar situation. A V final, thank you. Candy for you. I'd be asking you to find V final. Yeah. Candy for you. Well done. Okay? Last thing. Okay? Oh, heck. Now, there's two types of work questions. First one is lifted up to oh heck, let's do an altitude of twice twice the radius of the Earth. How much work will this take? Clay, what's this question asking me to find?
Work.
Is it mentioning orbit?
No.
So what that means is we're lifting it straight up, we're launching it straight up, we're asking how much fuel, it's going to come crashing back down. What that really means is this. There's my generic work equation. Because we're not going in orbit, I can assume that. What's changing anything? Negative big G, big M, little m all over R final minus negative big G, big M, little m all over R initial. Now I need to read this question, Kohei, very carefully. Here's what it's telling me. It's telling me that the altitude, there's the satellite, the altitude is twice the Earth's radius. How far is the distance from the planet? I think R final equals 3 times our Earth, right? 2 above the planet plus 1 more. R initial is going to be our Earth. Is that okay? Now it's plug and chug. I mean, complicated plug and chug, but plug and chug. We're going to use ditto marks. We're going to be really, really clever. So it's going to be negative 6.67 times 10 to the negative 11. Mass of the Earth. Mass of the satellite, 9650. All over 3 times the radius of the Earth, 6.38 times 10 to the 6th. Plus, same thing times same thing times same thing, all over radius of the Earth. Hey, Colin, what do I call those vertical lines? These little hash marks here? Sorry, Colin. I said Colin. Kyle. Sorry? Ditto. Brain dead moment there. How would I type this in? And again, you can type this in all in one fell swoop. It just lends itself to lots of typos. So what I tend to do is negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 9650 divided by bracket 3 Earths. Here's my final. Negative 2.011 times 10 to the 11th plus the initial is going to be almost the same. I just delete the negative. And I guess this one's really nice. I just delete the 3 times, don't I? It's kind of convenient. Yeah.
How'd you go back a row on that calculator?
Left arrow. That'll do it. I haven't figured out how to go back 2 or 3 rows. I know there is a way, and I used to know how, and I haven't used these for long enough that I've forgotten. But if I do, I'll let you know. But back arrow lets you go back 1 line. Left arrow. Okay? 6.033 times positive 6.033 times 10 to the 11th. So how much work? That plus negative 2.011 times 10 to the 11th. That's how much fuel it would take to get there. Okay? Is that all right? Oh, units. Joules. B. What if we want the satellite to stay in orbit? How much work will this take? Okay. You okay? Now I'm doing you a favor because we've already done, no pun intended, most of the work in finding how much work. We would start out by going why don't I cancel out the change in kinetic this time? Because in orbit you have an orbital speed. You have kinetic energy. Thankfully, the change in potential is 4.022 times 10 to the 11th joules. We've already done that. Yay! Thank goodness. Is that okay so far? Yeah. So now I would have no problem making this one question where you have to find this and then find this, but here I'm going to combine the 2 of them. In fact, I know on the test I did make it one question. I'm suddenly realizing this would be a nicer way to do that. Next year I might do it this way. Find how much work to lift it up, then find out how much work to keep it in orbit, and you can use the same answer.
So in the test, you just go straight to how much you can learn it?
No, I'm saying next year I will, but this year I can't. I think this year, I photocopied the test a couple of weeks ago. I think there's one question where you're just lifting it up, like we just did. It's going to come crashing down. And then there's another question where you're putting it in orbit. Okay? Which means you'd have to find that. Colin, what's changing anything?
Final answer.
And we'll assume worst case scenario that your initial kinetic is 0, even though technically you're on a moving Earth and you can get a boost from the Earth, but that's yucky math. So this is going to be a half mv final. Which v? V orb squared. They didn't tell me v orb, but I can figure it out because gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals mv squared over r. So we need to find v orb to do this. One of the r's cancels. Kiowa says a mass cancels. And normally, Lewis, I would square root, but I can't help noticing that v squared is actually what I want. So rather than square root, I'm just going to take this, stick it right into there. That's going to give us a half little m, big G, big M over r. Which r? I think since we're putting in orbit, our orbit. And I think, no, this is where I would love to be able to backspace 2 lines. If I can get to that line there, it would sure be nice. It's going to be equal to, I got to type this from scratch. 0.5 times, what was the mass? 9650, I think? Times 6.67 scientific notation, negative 11, times 5.98 scientific notation, 24, divided by the orbital radius was 3 Earths. There's your change in kinetic.
It's supposed to be like to the 11th, 10th, or 9th, right?
Generally, if you're around the Earth, and I'm not having you go out like past Pluto, yeah. I'm pretty sure on your test you'll end up with 10 to the 9ths and 10 to the 10ths for work-related questions. 1.0055 times 10 to the 11th. So the work is going to be 4.022 times 10 to the 11th plus 1.0055 times 10 to the 11th. Is that what it was, Mr. Duke? .03 times 10 to the 11th. That's how many joules of energy it would take to put this satellite in orbit. By the way, that doesn't count how many joules of energy it would take to put the fuel that you would be burning to put this in orbit. You would then need the mass of that, which would add more. Of course, then you need more fuel. Calculus students, this is a classic, fairly difficult related rate problem, because the more fuel you add, the more mass you've added, the more fuel you need. There is eventually a magic break-even point where you've got enough fuel to cover your satellite and all the fuel that you're burning. It's a lovely derivative equation. That's 99% of what you're gonna see. So now I pause and I say, questions from the review, questions from the homework, anything else you want me to go over? Now is your chance to ask. Colin.
Lesson 6, number 15.
Lesson 6, number 15. I don't think I put frequency on the written. I might have put it as a fairly obvious multiple choice, but I can't remember now. Lesson 6, number 15. This one here. So easy that it's tough.
I
Okay.
like that one.
What does it want you to find? Okay,
if you
total.
infinity.
If Vikas has $10 and you have $40, what do you total between the two of you? What does the word total mean as a mathematical operation?
Add.
If you add that number there to that number there, that's the total energy in orbit. Oh, and Colin, before you get all groany on yourself, look up, look up, look up, look up. Remember I said there was actually a shortcut. We did notice a neat pattern. When you're in orbit, your kinetic energy is half of the potential energy but positive, and the total energy is actually the same as the kinetic energy but negative, which it also all is there. Do you see what I meant? You were making that so easy that's tough? Yeah. You don't have enough information to find anything else. The kinetic energy, I still need the mass of the satellite to find V, then I could find how high it is, but is that all right? Next! Someone else had a question, I thought, or Colin can ask another one. He's scared too, no. No, that was a good question. Yeah.
Can you give us an example of that written one you like us to do, where you have to explain the difference?
No,
Like the-
I've dropped many things, hints about it during the unit.
Okay, fair enough.
Usually the using principles of physics right to explain involve rants or tangents that I've gone on more than one occasion. And that's one of the ones where I am, trust me, it won't be a surprise, but what I'm really saying is, can you, knowing what the answer is, give me an eloquent proof of what the answer is? Those are what I like.
No, it's not gonna be a Ferris wheel.
Question back there? Colin, you have a question.
It's gonna be.
I saw your hand.
One of your other reviews that I watched for the last unit, he just went through here and just basically said what the 20 or so.
Oh,
key-
I'll go through my written and just my. Okay. Any more questions first before I go through the actual? I like this question. I like this question. I like this question. We'll stick.
I didn't bring my thing.
You can write down the questions on a piece of paper.
That's smart.
Is that what you get paid the big bucks?
Well, relatively. I think on the salary hierarchy of things, we're middle class, my friend.
Make living me either. Cause I'm poor.
Yo, I can't really learn lessons like.
Questions that I like. Certainly, folks, something like number 1 in that on the multiple choice section, there's going to be a conceptual question or two. Are you with me? Write this down if you need to. In that, I need you to know if you're moving in a circle, what direction are you accelerating? What direction is the force? Towards the center. What direction is your velocity? Not towards the center. Tangent to the radius. Okay? So there's several of those on this review, and I'll say I like any one of those because I'm going to somewhere either ask that as a picture like this or in one of those 2-column charts, go down each column with X's and check marks and then read across to circle the correct answer. So number 1, totally fair game in my mind. Number 3, I like number 3, I like number 3, I like number 3. Number 4, conceptually, this is how we, sorry, you know what? I'm going to take that back. Number 4, I'm going to take its gravitational field strength. If number 4 was looking at work, where you had force and distance, because that's how we derived our energy equation, that I would like. So I'm going to say, hang on, number 4. Number 5 is just a nice concept. Number 5 is saying as R gets bigger, what happens to V, what happens to T? You know what? If you start out with gravity is what's pulling me in a circle, and you decide to get the T by itself, or you get the V by itself, ask, well, who remembers the equation for V? The equation for V was, I got it back here somewhere, right there. As R gets bigger, as you go further out from the planet, what happens to your orbital speed? Gets bigger, smaller, or stays the same? I heard someone say bigger, I heard someone say smaller. The good news is someone's right. Ty, where is the R, on the top or on the bottom of this expression? So as this gets bigger, what happens to your overall answer? Because you're dividing by a bigger number. In fact, I could even be more specific. It gets smaller by the square root of the radius. So if you get 4 times further out, the velocity is half as big. I'd have to walk through it. But anyways, and it's true, the further out you get, the less kinetic energy the satellites need. They don't need to be going as fast because they're further from Earth's gravity. What about as R gets bigger, what happens to the period, the length of time it takes for them to go around? as this gets bigger, what happens to how long it takes them to go around it gets way bigger by a cube. Okay? So those would be nice, some conceptual stuff like that I would have no problem with. That might be, Clay, a good using principles of physics right to explain question. Oh, the satellite radius is doubled. Will you need more kinetic energy or less kinetic energy? Convince me, using principles of physics, or something along those lines.
Do you like it?
I think I just said, yeah. I just did a 5-minute rant on it. I think that would be hint enough. Colin, going back to the question that you asked me earlier, the one that I said that was so easy that it's tough. So this one here is just asking number 6, and I'm not saying I like this question. In fact, I don't like this question in that I told you you could survive without it. But just to answer it, I know that the kinetic energy is half of the potential, and the total is half of, but positive, and the total is half of the potential, but negative. A is the only possible correct kinetic, potential, and total energy because it's the only one that matches that pattern. If you're wondering, I think I said to you when I taught you that shortcut, there was a couple of questions on the review where you had to use it. I'm not going to give you a question on your test where you have to pull that out of your back pocket. You'll always be able to get there the long way. There may be one where you could use that shortcut to save yourself some time, but you won't need it. Sure, number 7 is fair game. The only thing I don't like about number 7, what's number 7 asking me to find? Really, I'll say how much work. Okay, because work is energy is the ability to do work. I would phrase it that way, but totally fair game. In this one, are they being put in orbit? No. So work is just going to be the change in potential. Use the cosmic potential. It's an asteroid, so make sure you use the numbers for this mystical asteroid here. There's the radius. There's the mass. Oh, Clay, is this an asteroid? Say yes.
Yes.
I doubt you're going to get 10 to the 9th or 10 to the 10th in your answers. I think it's going to be way smaller. But that's a totally fair game question. 8 is totally fair game. 8 is totally fair game. So I like number 8, I like number 8, I like number 8. I like number 11, I like number 11, I like number 11. No, I take that back. Sorry. I like number 12, I like number 12, I like number 12. I like number 13, I like number 13, I like number 13. Number 13 is a bit of a twist because instead of asking you to find the energies, they're giving you the energies and saying, okay, in one of those energies, you can get the big M by itself, the mass of the planet. Okay. I like 14, I like 14, I like 14. I like 16, I like 16, I like 16. Hopefully 17 is obvious. Why can't I use MGH for calculating orbits and satellites? Okay. In other words, don't do that. I'm not going to ask you a conical pendulum, so number 18 you could truthfully probably skip. I like number 19, I like number 19, I like number 19. '20 is good, that's conceptual. I like 23, I like 23, I like 23. This is what I was trying to get. You should know that the other way that you can find the potential energy, it's the area from the radius of if we have the gravitational force of the planet, it's the radius of the planet as you move further and further away. This is how we derived that equation or defined that equation. So it would be A3, and out to infinity. How much energy do we have out on infinity, potentially? How much potential energy do we have out on infinity? 0. We've defined it that way, relative to 0 at infinity, which is why coming in closer it's negative. Sure, 25. 25 is a fairly tricky one, but it's going backwards. What's it asking you to find? The mass of the planet, and they gave me all of the energies and the radiuses, so going backwards, find big M. There's probably going to be a question somewhere where I have you find the mass of a planet. 26 is good. I like 26. I like 26. I like 27. I like 27. Although this is only asking you to find a free body diagram, I would probably, if I gave this to you, then also ask you to do something with it. I'd give you some numbers and crunch.
How many questions are there about?
I don't know. Just hang on. Come back to that. I like 30. I like 30. Now 30, don't let it overcomplicate you. What does number 30 want you to find? Which force? The net force of? The net force of Ty? This is asking you to find Fg. G, big M, little m, over r squared. Don't overcomplicate it. This is what Cavendish set up. But, okay. 31A is good. Oh, sure. And 31B, here would be an example of using principles of physics. As r gets bigger, what happens to the speed? And I think we said that as you go further out, it's less than. And as a lovely proof, I would derive the equation for v. The r is in the bottom, and I would just say, as r gets bigger, v gets smaller. Something like 33 is conceptual, but again, make sure you know the difference between which way it's accelerating. It was accelerating towards the center, but which way is its velocity? Direction 3 in this case. .36 is fair game. They're giving me the period and saying find the radius. Gravity is what's pulling me in a circle. Uh, 38 is kind of nice. First of all, 38A for 2 marks wants you to find the acceleration due to gravity. I think dropped means VI is 0, VF is 15, T is 4. You can find little g. But that little g, the acceleration due to gravity, is also little g, the gravitational field strength. Now you could say little g equals big G, big M over r squared, and you could find the mass of Mars. So that's fair game. 39, that's that conical pendulum. You can nuke that. 40, you can skip. It's that conical pendulum. 41 is fair game. 42 is fair game. 43, absolutely. .44 is fair game. 45 is straight plug and chug. It wants the acceleration, v squared over r. Not mv squared over r, that's a force. Acceleration is v squared over r. Yeah. .49 is fair game. What are they asking you to find in 49? Oh, just the change in the kinetic energy, which would be a half mv orbit squared. I think you'd have to find v orb. Gravity is what's pulling me in a circle. Okay. I don't know why number 50 is a scholarship question. They're giving, first of all, what are they asking me to find in number 50? Height. Is there a change in height? Is there a change in speed? This is a job for conservation of energy. Your final kinetic energy is 0 because you're slowing down at the top for a split second. You're at 0. It's the moon. I'd make sure I use the mass of the moon. It's very doable. I don't know why that was a scholarship one. I would consider something like that fair game. In fact, I like the moon better than the Earth because in the moon, no air resistance, so you are actually way more accurate. Oh, and it's the moon. So I'm going to argue 50, totally fair game. .51 is cool, but a little overkill. See again. 52, to me, they're giving me the mass of the planet, the radius of the planet. There's my R initial. They're giving me the initial speed. Find the height. I think that's fair game. I think it's tough because the R is on the bottom of that fraction, and yet we have to do some yucky math. But I would consider 52 totally fair game. "12 is tough. Not fair game. Really cool, though. Sorry, 12 marks. 53, 53. I was looking at the 12 marks. This one, what does this one want you to find?
Gravitational field strength.
I think it wants you to find little g, which,
Big G people.
well, remember the roller coaster, little g canceled? Oh, wait, though. This time the normal force doesn't cancel, so little g won't cancel. You'd end up getting little g by itself. I don't think you'd use big G, big M. I think you can get it straight from using potential energy and getting little g by itself, I think. Look at my answer key online. I think that's what I probably did. 54 is overkill. Cool, but overkill. 55, nah. Other questions that I like. What, Mr. Dewick? Other questions that I like. From lesson 2. From lesson 2. Definitely like question 2 and 3. 6 and 7, conceptual. Oh, there it is. 9. Well, 9 and 10 are the same question. I decided rather than do a spinning spaceship this year, I'm going to do amusement park rides. I might do a spinning spaceship next year. So it's either going to be 2 of roller coaster, Gravitron, and Ferris wheel. 2 of those 3, right? 12. Oh, I really like number 12. Because it says both finding a little g and finding a mu. That was from lesson 2. Questions I like from lesson 3. I hope there's a roller coaster Ferris wheel here. Sure, 70. 77. 75. 7. Number 9. The only thing I don't like about number 9, it's 55 kilometers per hour. I would give you it in meters per second. I'm not going to try and trap you with units on the test. So also, I went through it this morning. There's no kilometers on the test. They're all in meters. Lesson 4, gravitation. Certainly something like number 1, asking you to find a force, but, and I would have no problem giving you the force, the radius, and one of the masses, find one of the other masses. In other words, anything in this equation, big G is constant, but if I give you any one of 1, 2, 3, 4 things, you can find, if I give you 3 of the 4 things, you can find the 4th one. Gravitation, something like number 7, gravitational field strength. This is a cool picture, but I'm not putting this one on your test. The whole hanging mass and something going around in a circle. I don't think it's on your test. Now I've got a sneaking suspicion that I may have just lied. I'll come back to that. Hang on.
So why don't you show us the test? We'll discover that for ourselves.
Lesson 5, orbits. So you should certainly understand, number 1, why satellites don't fall to Earth. They do fall to Earth. Why don't they hit the Earth? Because they miss the Earth. They're always falling to the Earth, but we give them just the right sideways velocity or speed so that they're continuously falling but never getting any closer to the Earth. Something like number 3. So you got to be able to find an orbit. 10 was a little overkill. Sure, 13, 14, 12, 13, 14, totally, I love it. Definitely there's going to be a written question where I give you one of radius, orbit, or speed, and I ask you to find the other 2. Okay. Lesson 6. something like number 3, except not in kilometers. Something like number 7, where I want you to find how fast it hits the Earth. Both, this is a change in height, change in speed, conservation of energy question. Something like number 11. 14. So asteroid impact speed. You're all still freaking out about Apophis, right? Hopefully Colin now sees 15 as right, straightforward. Number 7, orbital mechanics. Sure, something like number 3, totally. I'm giving you the kilometers from the moon center, times that by 1,000, and you do have the radius. You should be able to find orbital speed, orbital potential energy, orbital kinetic energy, and total orbital energy. Sure, that works. Definitely something like number 5, E. How much you're going to be asked how much work to put something in orbit. Sure, something like 7 or 8 is fair game. Conservation of energy. But really, if you work your way through the reviews, the big ultimate review, you're in really good shape, with the exception of, remember, I always reserve the right to go backwards. Oh, this time he gave me the orbit, and he gave me the radius, and he gave me the speed, and he wants me to find the planet mass. I'll get the big M by itself when I go gravity is what's pulling me in a circle. Fair game. Or he's asking me to find, I don't know, whatever. That's always fair game. Let me pause the video for 1 second. I'm also going to offer to print this up, but just hang on.